In the last video, we looked at how we could derive a rate expression from experimental data. Rate expressions are great because they could tell us how reactants can affect how fast a chemical reaction goes. But more importantly, they tell us what's going on at the microscopic level. Which particles are likely to react with which particles in the reaction. The reaction that was studied in the last video was the iodination of propanone, where iodine reacts with propanone under acidic conditions. And a variety of experiments were carried out, and it was found that the reaction was first order with respect to the propanone molecules, first order with respect to the catalyst hydronines, but the change in the concentration of iodine had absolutely no effect. It was zero order with respect to the concentration of iodine. So let's look at what we can deduce from the mechanism. Most chemical reactions take place in several steps, and each of the several steps contribute to what is called the mechanism. It's highly unlikely that at one point in time all of the propanone molecules collide with the iodine molecules and the hydrogen ions to result in a successful collision. Instead, it's highly likely that this takes place in steps. In any chemical reaction, the slowest step will control the speed of all of the other steps. They can't go any faster. And this step is called the rate determining step. So let's look at the reaction that we studied again. That's the iodination of propanone. Now this point is really important to make. In a chemical reaction, any step that occurs after the rate determining step, that's the slowest step, will not affect the rate, provided that it's really fast compared with the slowest step, the rate determining step. So species that are involved in the mechanism after the rate determining step do not appear in the rate expression. So let's look, for example, at this reaction here. That is the iodination of propanone. So let's now look at the species in the rate determining step, the slowest step, and then look at the rate equation. So here is hydrogen ions, and in the slowest step there are 1 mole of hydrogen ions colliding with 1 mole of propanone molecules. So the species that appear in the rate determining step also appear in the rate equation. So it's first order with respect to hydrogen ions, and there are 1 mole of hydrogen ions in the rate determining step, and it's first order with respect to propanone, and there are 1 mole of propanone molecules in the rate determining step. It's zero order with respect to iodine molecules, as these do not appear in the rate equation. They are in consecutive steps that appear really, really quickly. All mechanisms, therefore, are deduced by experiment and determining the rate expression. So let's revisit why we suspect that the nucleophilic substitution reaction between hydroxide ions and the halogenoalkane, why it will follow that the rate expression would involve hydroxide ions and bromomethane molecules, because if we look at the proposed mechanism, it's been proposed that the hydroxide ion donates a lone pair of electrons to the electron deficient carbon, and at the same time the carbon bromine bond breaks and the bromine leaves, taking a pair of electrons with it. This mechanism has been proposed because in rate studies it is found that when we carry out rate experiments, that the order of reaction is first order with respect to the concentration of hydroxide ions, and also first order with respect to the concentration of the bromomethane. Because both species are involved in the slowest step, or the rate determining step, it's first order with respect to hydroxide ions, because there is 1 hydroxide ion colliding with 1 molecule of bromomethane. Some textbooks call this an SN2 reaction, nucleophilic substitution, 2 particles involved. The old term for this was molecularity, and that was the number of particles involved in the rate determining step. So the molecularity of this reaction is 2, because there are 2 particles colliding in the slowest step, the rate determining step. Now let's consider a tertiary halogenoalkane. So this tertiary halogenoalkane here, 2,2-dimethyl bromoethane, which is a tertiary halogenoalkane, this can undergo heterolytic fission so that 2 species are formed, and one of them is a tertiary carbocation. And what we know about tertiary carbocations from GCSE is that they are more stable than primary carbocations because of this inductive effect where the 3 methyl groups can release electrons, stabilising this positive charge. With tertiary halogenoalkanes, the first step, the slowest step, is waiting for this heterolytic fission. And therefore, when rate studies are carried out on tertiary halogenoalkanes, it's found that the rate determining step is not dependent on the concentration of hydroxide ions. For this reaction, it's been found that it's 0 order with respect to the concentration of hydrogen ions. So if experiments are repeated where the hydroxide ion concentration is changed, it has absolutely no impact on the rate, because the first step, we're waiting for the heterolytic fission of this carbon-bromine bond to produce the tertiary carbocation. The second step in the mechanism, therefore, is when the hydroxide ion then attacks the tertiary carbocation, and this is going to be really, really, really fast. So let's now consider any general reaction where our reactants are A, B and C, and the products are Y and Z. So remember, the rate of reaction depends on the concentration of the reactants. So let's now look at this mechanism. So say, for example, in the first step, A and B react together to form an intermediate D. Notice that this intermediate doesn't appear in the reactants. And that tells us that the intermediate, this species D, is going to get mopped up in the next step. So in the next step, D could get converted to E. And E is a second intermediate, which again doesn't appear in the products. And therefore this intermediate must also be eaten up. So then E and C, these species here, could collide together to form Y and Z. It therefore follows that this slow step here is the rate determining step. The rate determining step doesn't always have to be the first step in the reaction. So it's important to note that any species involved in or before the rate determining step can affect the overall rate. So because these species, even though this step happened quickly, A and B were needed to produce this intermediate D, and therefore we can deduce that the rate expression for this reaction will be A, B and D. So the rate will be proportional to the concentration of A, B and D, and because there was 1 mole of each, it's first order with respect to A, first order with respect to B and first order with respect to D. So it's really important to note that the species in the rate equation are not just the reactants in the rate determining step, but they're the reactants involved in the reactions occurring before and in the rate determining step. So let's look at these scenarios for this chemical reaction here, where 2 reactants, A and D, following using a catalyst, produce product G. You can see that in scheme 1, first of all, A collides with B, which you can see doesn't appear in the reactants, to produce this intermediate C, and that is the slow step. It's quickly followed by C, this intermediate here, quickly decomposing into 2 other intermediates, D plus B. D then collides with another of the reactants, E, so it uses up that reactant there to form this intermediate F, and F quickly decomposes into G. You will notice in this, if we add all of these steps up together, A if we add all of that, comes down here. We notice that C cancels out here and here, and B cancels out here and here, and D cancels out here and here, and we can see that E and A, which are the reactants, appear now on this side, A plus E. Notice that F has cancelled out because it appears on both sides, and that leaves us therefore with G. So when you add up all of the steps in a reaction mechanism, each of the steps in the reaction mechanism, everything cancels out to produce the original reactants and products. You don't see these intermediates appearing in the overall balanced or stoichiometric equation. So let's first of all look at scheme 1. We can see easily on scheme 1 that this is the slowest step, and it's also the first step. So in scheme 1, therefore, A and B must be in the rate equation. So from this scheme 1, we could write a rate expression, which is rate is proportional to the concentration of A multiplied by the concentration of B. Now you can see that B does not appear as a reactant. Let's look at that later. Let's now have a look at scheme 2. In scheme 2, again, A and B are reacting together, but that's a really fast step. So it's not the rate determining step. They're making this product C. C then quickly breaks up this intermediate. So an intermediate, remember, is something that doesn't appear, it's a species that doesn't appear in the overall equation. So this intermediate quickly breaks up to form D and B. Now this here must be the rate determining step, or the slowest step, which involves this intermediate D and this reactant E. When D and E collide together, they produce this intermediate F, which also slowly decomposes to form the product G. So this is the slowest step here, followed by a second slow step here. So if we look at scheme 2 here, you can see that B and A react together quickly. Now B isn't a reactant, it's not appearing in the reactants, and therefore B must be the catalyst. Let's now have a look at part B. Which species cannot appear in the rate expression for scheme 1? Well, let's look at which species will occur in the rate expression for scheme 1. First of all, we have A and B, which are the slowest step, and therefore we have already deduced that A and B will appear in the rate expression, and therefore we can see that no matter how much you increase the concentration of C, it will not affect the rate. So species C can't appear because it's an intermediate, but more importantly, E is a reactant, and E also takes place in a fast reaction. So no matter how much you increase the concentration of E, the rate will not be affected, and therefore which species cannot appear in the rate expression? It must be reactant E. Both D and F are intermediates, and the intermediates never appear in the rate expression. Please check the typo in the caboodle book which says F. It should be E. Next question is really easy. Which is the rate determining step in scheme 3? Clearly it's the slowest step, and therefore it has to be step I, step 2. Quick pause point. Can you answer these questions? First of all, which one do you think is the correct definition of intermediates? are intermediates, the species that appear in the steps but not the net equation, the species that appear in the net equation, the reactants in the equation, or the phase the species are in. Secondly, what is the definition of the rate determining step? The slowest step in the reaction, the fastest step in reaction, the overall rate of the reaction, the step that determines the reaction. So, an intermediate is the species that you don't see in the net equation. It's something that's produced and then gets used up. So, it's the species that appear in the steps, but not the net equation. Well done if you got that correct. And the rate determining step is simply the slowest step in the reaction. So, let's now do some brain teasers. In a reaction between E and F, so let's write that down. So, we've got E and F forming some products. Says the reaction was found experimentally to be second order overall. Which of the following mechanisms is consistent with this, and explain your answer? So let's look at mechanism 1. Mechanism 1, you've got reactant E decomposing to form intermediates. Notice these are intermediates, they don't appear in the rate equation. And then that combines Y, then this intermediate quickly decomposes into another intermediate reacting with F, one of the other reactants. But that's a fast reaction. So immediately I would deduce from this that the rate expression is simply first order with respect to the concentration of E because it's in the slowest or rate determining step. So that's not second order. In mechanism 2, E and F are involved in the slowest or rate determining step. And therefore from that I can deduce that the rate expression is concentration of E first order, because there is one molecule of E, multiplied by the concentration of F, which is first order with respect to F. And since there are two molecules in this, it's bimolecular, and we add the two orders together, so that one is second order overall. Let's just look at mechanism 3. In mechanism 3, we have got two molecules of F, which is the slow reaction, and therefore I can deduce that the rate is equal to K, but because there are 2 moles of F colliding, two molecules, it's second order also with respect to the concentration of F. So it says here, which of the following mechanisms are consistent with this? So mechanism 2 and mechanism 3 are both second order.